L'Hopital's or Bernoulli's rule. L'Hopital was born in 1661 and died in 1704. He was a French mathematician that published this rule in 1696 in what is considered the first differential calculus textbook of the history, which is Analyze. Years later, it was proved that L'Hopital was closely tutored by a known mathematician, doctor and philosopher, Johann Bernoulli, who after L'Hopital's death came up with the truth that L'Hopital paid him off to use his discoveries, including this rule. But that is not actually the point of this video.
Now we will talk about the indeterminate product forms, which is when you get like 0 times infinity, so that you can apply the next formula, so that if x times gx can be equal to the limit when x tends to any number of the function over the other function, or equal to the other function over the function. It depends on what is your convenience to do. Now we are going to do an example of the indeterminate products. The example is limit when x tends to 0 of cotangent of 2x times sine of 6x. If we substitute 0, we get that sine of 0 is equal 0 and cotangent of 0 is equal infinity. Imagine the graph. So we get an indeterminate product here, and we can apply the formula. And to get sin of 6x over tangent of 2x, we use the identity of cotangent of 2x, that it's 1 over tangent of 2x, and that then we substitute again the 0, and it gives us that sine of 6x or tangent of 2x is equal 0 over 0, and it is still an indeterminate form. So we can apply the Hospital rule now. If we derivate sine of 6x, it gives us 6 of cos, 6 times cos of 6x, and if we derivate tangent of 2x, it gives us that is 2 times 6 secant squared of 2x. Finally, we need to substitute the x, and so 0 times 6 and cosine of 0 it's equal 1. Then x times 2 equals 0, secant of 0 is 1, and 1 squared is still 1. Finally we get 6 times 1 over 2 times 1, that it's equal 3, and that is our result.
Well, the second type of indeterminate forms is indeterminate differences. And as its name says, indeterminate difference takes place when we evaluate the limit that x approaches a of a difference of functions, in this case f of x minus g of x. When we evaluate the limit, when we substitute a, we might get infinity minus infinity. So when we get this result, we have to transform this difference into a quotient, an appropriate quotient, in which we can apply L'Hopital's rule. Let's see this example. The limit when x approaches 0 by the right of 1 over x minus 1 over e to the x minus 1. There are two ways of evaluate evaluating this limit. One is by putting into the calculator close numbers to 0, for example 1 over 0.000001, and we see that if we increase the number of zeros, the result is gonna be bigger. Another way is to evaluate or see its function, its graph. For example, the graph of 1 over x is this one, and we see that when the graph approaches 0 by the right, it tends to go to infinity, and in the other side, the graph of 1 over e to the x minus 1 has the same case. When the graph approaches 0 by the right, it goes to infinity. So we get infinity minus infinity. So we have to make an appropriate quotient for this difference. So we do this difference, we multiply the denominators. 1 times e to the x minus 1 is e to the x minus 1 minus x. We solve for this, and we take the derivative of the numerator and the denominator. Then, well, the derivative of e to the x is e to the x minus 0 minus x. That is 1. This is a product, so it's the first term times the derivative of the second one plus the second one times the derivative of the first term minus x, which is 1. We simplify and we substitute the limit or real close values to 0, and we see that we obtain 0 over 0, another indeterminate form. So what should we do? We have to apply the L'Hopital's rule again, which is the derivative of the numerator over the derivative of the denominator, which is e to the x minus 0 times the first term and the derivative of the second one plus the second one times the derivative of the first one plus e, and the derivative of 1, which is 0. We simplify and it gives us e to the x over x to e to the x plus 2e to the x. So now we see we can substitute close values, and we get that it goes to 1 over 2, which is 1/2. And if we see its graph, which is this one, we see that when the graph approaches 0 by the right, it goes to 1/2, which is this value.